So if you're interested in a summary of the slides that I'll show today, there's a summary here on the Twitter feed along with links to some of the research that we'll talk about today if you want to look in more detail at the research papers. So I'm a cognitive scientist, and I study visual thinking and visual perception. And let's maybe pick on Matt for a second. So Matt, duck or rabbit? OK, but you can see both, right? Yeah. So we, in the visual perception land, study stimuli like these to show how messing with the knobs and the switches in your head can cause you to take one image and interpret it in many different ways. And this is called an ambiguous figure. These actually, this is the vision scientist's dirty secret, is that these actually rarely happen in the real world. These are largely a construction in the lab, and it's hard to find real-world stimuli that cause this same tension in your head because your object recognition system is so finely tuned and so good at what it does. I did finally find an example in the real world where this did happen. So when I look at that bag dog thing, it actually takes me a full 5 seconds, regardless of how many times I've seen this, to decide whether it's a bag or a dog. It is a bag, after much staring, I've decided. So these ambiguous figures are not very prevalent in the real world, but in visualizations, these are ubiquitous. You can look at the same visualization and see many possible patterns in the data. Visualizations are a form of ambiguous figure. What we want to do today is to look at least 3 different visual tools that you have in your head, ways of turning those knobs and flipping those switches to see the patterns in a data visualization in different ways with different parts of your visual system. Eventually, we want to get here. This is where we hope to be, but talk to me in 10 years. We want to be able to say, when you look at complex real-world visualizations like these are the different ways that you can see patterns in them. Here's the complete list and most likely priority with which somebody would step through all the patterns in these data. 10 years, maybe. 5 years, maybe. We'll get to something like this. For the moment, I want to show you that even in the world's simplest data visualization, we're just going to be here for a few minutes, you can still see at least 3 types of patterns in these data using 3 distinct visual tools. This is going to be our fruit fly. We're going to test on this simple model of how the visual system interprets visualizations and then scale up once we understand this simpler problem. So using these just 2 bars, we can apply at least 3 visual tools. One's going to be object recognition, so you can recognize this thing in the same way that you would a face or a house or another object in the real world. So it kind of, if you squint, it kind of looks like a house with a sloped roof. You can use another system that allows you to pull distributions of features out of the world. You can notice this and see that there's 2 different sizes. There's a big one and a small one. Finally, there's a third system that allows you to draw comparisons out of individual objects, to notice that the one on the left is bigger or the one on the right is grayer. Critically, we'll go into each of these 3 systems in more detail, but the important division between them is going to be that the 2 on the top operate extremely quickly. In around 100 milliseconds, you can recognize an object, or you can pull out feature distributions from the scene in front of you. The one at the bottom takes on the order of seconds to pull out these individual comparisons, which act like sentences that you have to say to yourself in your head, even in your visual system. Here's going to be our model of the visual system. We're going to set up sort of a dashboard of what it looks like from inside your head as a metaphor for the tools that we have available. In the middle, we have your portal into the world. On the left side, we have your object recognition system, which we're going to treat as a gross cartoon for today. So your object recognition system is this hierarchical neural network that represents potential objects in this vastly multidimensional space. And it operates pretty similarly to the way that the DeepNet that Sean showed this morning operates. And the point of this system is that it can only recognize objects that you've seen before. That's the power, but also the limitation of this system. So we're not going to talk about how it works. We're just going to say something appears in the world, and you get a constellation of activation that lets you know that that's that thing you've seen before. So using that object recognition system, let's see how you do, or how the typical person would do, on interpreting data. This is a problem from the graph comprehension literature that's given to high school or college students. And you'll notice that the y-axis is position and the x-axis is time. And you can ask the student, here's a graph of an object's motion. Can you give me some example in the real world of an object that would create the data on this graph? And I'll give you a moment to think in your own head what you would say. I won't call on anybody. But what the typical college student will say in many of these, for graphs like this, is that this is an example of a ball rolling down a hill. So there's something rolling, and then it goes down, and then it goes down again. Or it's someone walking at a mall, and they go down an escalator, and then they keep walking, which, so you figured out by now, is wrong. What you need to do is to stop object recognition from firing and leading you to that automatic association that it looks like something in the world, and do something really different. Use a different visual tool. Visual tool you want to use is to slice this function up into 3 separate lines and say in the orange section, there's an object that's not moving, but time is moving. And in the green section, both are moving, which means that the object is moving in some direction. We actually don't know what direction. And then at the end, in the blue section, you have an object that's not moving, but time is passing. So there's an object, it's still, it's at rest, it moves, and then it's at rest again. Really different interpretation from the one that your object system gave you as a knee-jerk reaction. So that's a way of using object recognition to analyze data with your eyes. So you can imagine looking at this and saying it looks like some sort of a little house with a slopey roof. We're not sure how far that's going to get you yet, so let's move on to the next tool. The next tool is going to be feature distributions. You can pull out the distribution of, let's say, sizes in the world. Here's why you need that system in the natural world. You have object recognition on the left, and let's say this is what you see out in front of you. You can tell that you're on a beach, right? But this is actually some work from some computer vision researchers where they averaged every beach on the internet with some alignment. Notice that object recognition is not helping you out very much here. You have another system that gave you that statistical snapshot of the image that lets you recognize it as a beach. So you can compute distributions really quickly of different sizes, luminances, orientations, and hues of objects in the world. You can notice that it's pretty bright out, that there's a lot of horizontal lines, and that there's a lot of brown and blue colors out there, and that fingerprint of activation tells you pretty quickly that you're probably on a beach. This system also operates on the order of magnitude is about 100 milliseconds. So there's your window into the world. You have object recognition, you have the world, and you have feature distributions, and this is going to be our starting point. You also have some other features that you can compute distributions over, things like number and density. Just want to mention this isn't the exhaustive list, but we'll leave those off for now just to keep things simple. Let's put another picture up on the world. So this is what you're looking at. You can get some natural world information from this pretty quickly. You can notice that there's berries from object recognition. You can notice that there's big things and small things, big berries and small berries. You can notice that there's blueberries and red berries. So within 100 milliseconds, you have a rough idea of the statistics and kinds of objects that are out there in the world in front of you. And you're going to use these same systems when you analyze data. You're going to turn this into a scatter plot, and you're going to notice that there's circles out there, and that there's big ones and small ones and blue ones and red ones. And that's a great way to initially parse this data visualization into its component parts. We have a review paper together with some other data visualization researchers on the way you can use this system for natural statistics in the real world to compute statistics on data in visualizations. Let's imagine that there's these 4 operations you might want to compute on your data. You might want to tell what the mean of this cloud is, and you can do that really quickly with your visual system because you're really good at looking at the center of objects in order to get them to be closer to your retina, so you have a system that helps you do that. You can tell quickly that there's an outlier in the second display. You can tell quickly that these points go up as they go to the right. And you can tell quickly that there's 2 clusters of data here. So those are 4 typical operations you might do on these. You can do the same operations in each of these other feature distribution dimensions. So you can tell immediately that the mean color in this display is a light blue, that the dark blue is not like the others, that they get bluer as they go to the right, or that there's a bimodality in hue. You can tell immediately that the mean orientation, surprisingly precisely, you can tell that it's about like that. You can tell that one of these is not like the other. You can tell that they get straighter as they go righter. And you can tell that there's a bimodality in orientation space. In size, if you held up your fingers right now, you could tell me the average size of those circles pretty quickly and pretty accurately. You can also say one of these is not like the other. They get bigger as they go righter, and there's a bimodality in orientation space. So there's many statistics that you can pull just from your visual system's natural way of pulling statistics from the world. And in this paper, we talk about where the power of those systems are, and also where some biases might come in, where the types of mathematical statistics that you'd want to run don't necessarily match up with the sorts of natural scene statistics that your visual system is good at, and where that could lead you astray. And we also talk about some real-world visualizations and how the patterns that you can unpack on these real visualizations are in large part supported by that visual statistic machine that you have. And this is all work with Danielle Saphir, Steve Harrose, and Mike Gleischer. I'll give you an example of how you can depict data in two different ways and use two different systems. So if I showed you sales over time or widgets produced over time with a color heat map like this, and I said, what are the sales on July 22nd? You'd say low, right? So you know that you shouldn't do this because it's a low precision representation, and you'd say, get that out of here, show it to me on a reasonable visualization, give me something like that. And now you've got precision back. So if I said, what are the sales on July 22nd? You could say, where's July 22nd? And 32, and you can give me a more precise answer. You can get precision for other tasks. I can say, what month contains the single day with the highest sales? And hopefully you'd be able to pick out October pretty quickly. But pulling statistics out of this can be a little tougher. So what if I ask you, which month has the highest sales on average? Which is purposely not the one with the highest sales as a peak. That's a bit harder. Some of you are, I think, picking out August as the possibility, but it's a lot easier up on top when you can use your visual statistical system. So when you have just the line graph, you can pull out shapes and points and edges, and that facilitates some operations like finding peaks, but this is using the system that you would use in the real world to grab this object or understand its shape envelope. And that's good for some things, but not others. But if you use this heat-coded representation, then it can be much easier to pull out these sort of statistical properties of the data as opposed to the precise properties of the data, which we found a bit surprising. That's feature distributions. The third tool is going to be making comparisons between objects, and this is the slow one. Let's go back to our berries. When you're looking at these berries, you know that there's berries, you know that there's small ones, you know that there's big ones, you know that there's red ones, you know that there's blue ones, but how do all those features go together? I'm going to cover up the scene for a moment so you can appreciate the view from under the hood of your visual system. You know that all these features exist, but you don't know if the blue ones are big or small, or the red ones big or small. You actually don't know from this activation. This is a common problem that occurs in neural networks in general. It's called the binding problem. You don't, even when we make the scene simpler, we're just going to cut it down to two berries. You still don't know, are the blue ones small and the red ones big, or are the blue ones big and the red ones small? The pattern of the representation in your head doesn't support knowing which one of these go with the other. You also don't know which one goes where. You know, maybe even if you knew that there's big blue berries, you don't know whether that's on the left or the right of the scene. These are all representations, the ones of space, the ones of color, the ones of size, the ones of berries, that are scattered throughout your brain, and there's no way to link them together. So one solution to this problem is to effectively only look at one thing at a time. So if we pay spatial attention to both berries at the same time, you just isolate your percept with like looking through a tube onto just these two berries, you still have the problem. But now let's put our attentional spotlight just on the left berry. So you're activating information from that location in the world, relatively inhibiting other information from other parts of the world. So you're effectively only seeing the blue berry at once. No problem now. I know I'm on the left, it's a berry, it's big, and it's blue. So now you've solved that binding problem by not making it a problem anymore, by only looking at one thing at a time. And now we can shift over to the red berry. Got it. That one's small, and it's on the right, and it's red. So we've solved this problem, but you can see how this is a rather inefficient solution. It's going to require that you move your eyes or your attention around over time in order to solve it. That's going to take time. I'm going to make this problem even simpler. We're going to get rid of the berries, we're going to get rid of the different sizes, and just have color in multiple locations. In this case, there's a blue and there's a red. We know that from the histogram, but we don't know whether it's blue-red or red-blue until we do something like this. Shift your attention over to the left so that you're only on the blue thing. Got it, that's blue. Got it, that's red. So you're moving your attention around over time in order to be able to flexibly see any possible combination of features that could occur in an object. Why can't object recognition do that? Well, if object recognition did that, if you had an existing entry in object recognition for every object that you could ever possibly see, pink unicorns and blue elephants, then your head would be the size of this room. You don't have enough power in your head to have separate existing representations for everything you could possibly see. This is your visual system solution. You're looking at this and you're saying, Steve, you're crazy. I can look at this in one shot and I can see what's happening. I can see that it is red on the left and blue on the right. All right, well, I'm going to prove to you that it's actually a little bit harder than you thought. So we're going to play which one of these is not like the other. It's a little harder than you thought, right? There's one, right? So it's something that you're doing that's a little sluggish in this display. And what we think it is something like if you try to do this, you can't get these relationships. You have to do an operation that's like this, where you're moving your attention around over time until you figure out that in that case, the blue is on the right. This is not a color perception problem, by the way. Which one of these is not like the other? No problem, right? So there's nothing about the display that's causing this. Here's another one. It's your ability to parse the relative relationships between these objects. There's one, and there's one. This, by the way, this problem of who's on the left or the right or the top or the bottom, figuring out how the visual system parses spatial relationships between objects, is really important to our lab and many other labs because spatial relationships are the core of all this. All of these maps, graphs, diagrams, and data visualizations will arrange data out there abstractly in the world into spatial relationships between objects. So figuring out how your visual system extracts those relationships and how to get it to do it better is an important problem to solve in vision sciences. Let's go to a data visualization, our world's simplest data visualization. And in this data visualization, I'm going to claim that you can't process that arrangement in one shot, that seeing whether it's big, small, or small, big. If you pay attention to both bars at once, you're going to know there's a big thing, and you're going to know there's a small thing, and you're not going to be able to know whether it's big, small, or small, big, which is sort of important for interpreting the data here. So I'm going to predict that we're going to do the same thing. You move your attentional spotlight to the left, you know that that's a big thing, and you can move it to the right, and you can know that it's a small thing. Again, let's play which one of these is not like the other. This won't be as hard as the last one, but I think you can still feel that this is not instantaneous. You have to do some visual work to get the answer to know that these two are not like the others. One more. So the claim is, again, what you have to do is for each one of these, you have to pop through and extract this signal over time, and that's going to make your pattern perception, in this case, relatively slow. Because we're claiming that in order to know, even when there's just two bars, whether it's big, small, or small, big, you have to move your attention around. You have to pick off one of these with your inner spotlight or with your eyes. And so we're going to do an experiment. I'm going to show you how we collect data on these kinds of tasks in our lab. Our experiment's going to be, tell me whether it's big, small, or small, big, and we're going to predict that people are going to move their eyes around. To which, if you put on your reviewer 2 hat for a moment, you'd say, great, they're going to move their eyes around. Congratulations, that's really impressive. So we need a control task where we predict they're not going to move their eyes around, because people tend to move their eyes around a lot. The control task is going to be exactly the same display, big, small, big, but tell me whether or not these two things are the same size or a different size. You should be able to tell that just from your histogram on the upper right. If it's got 2 bumps, then they're different sizes. If it's got 1 bump, then they're the same size. So in fact, it should actually help to just keep your spotlight on both at the same time. So that's going to be our control task. We're predicting that people are not going to move around in that case. Here's the display, and by the way, this is all work from a postdoc in the lab who's moved on to a faculty position named Audrey Michael. And what Audrey's going to do is she's going to have you fixate in the middle. So here's where your eyes get parked. You can make decisions about these 2 bars or these 2 bars or these 2 bars. The ones on the side get complicated for today. I'm just going to show you the trials where everything's in the middle. And we are going to ask you, do you see big, small, or small, big? Or we are going to ask you, and in that case, we predict that you're going to move your attention around either to the big, to the small, we don't know ahead of time. Or we're going to ask you, are these two the same size or a different size? And in that one, we predict that people are just going to keep their eyes parked in the center because you can do this task holistically. By the way, half of the trials in this condition are the same size so that there's a point to answering the question, but we throw those out because we want what's on the screen to be exactly the same for comparison purposes. So I'm going to show you the data. I'm just blowing things up so you can see the eye movements a little bit better. We're going to show eye movements toward the taller bar or toward the shorter bar. So those could have been arranged like this, but I'm going to fold the data around like this so you're just looking at eye movements toward the taller bar on the left. For the same different task where we predict that people are going to keep their eyes in the center, it takes you about 600 milliseconds to answer this question, and this is what your eyes do. They largely just stay in the center. Now, same screens, we're just going to change. Oh, by the way, I'm going to let you see the pattern of data a little bit better just by expanding it upward. The vertical position means nothing. It's just a way of seeing the data a little bit better. Now we're going to change the task so that it's big, small versus small, big. And we're predicting that the eye movements are going to go either toward the tall bar or the short bar. People have idiosyncratic strategies, but the point is that they're going to be more divergent, and that's exactly what happens. You can see that these points line up. I'm going to connect them with barbells, so you can see individual people. In one half of the experiment, they have one task, and the other, they have another, and that's all counterbalanced. You can see that the black dots tend to be on the outside of the gray dots. I'm going to move these down so you can actually just see the distributions, so you can see the pattern a little bit better. And you can see that in the relational task, people tend to have this strategy where they pick off one or the other. These folks in the middle, they're not moving their eyes, but we'd have to predict that they're still moving their attention around. They're just good at using their attention in their periphery. So if we had an attention tracker, which there is a way to do with electrophysiology, then we'd have to predict that they're secretly moving their attention around under the hood. So this is, we think, an example of you using this comparison system up here, but the histogram system down here on the bottom. Two distinct tools of parsing this really simple data visualization. Some of you are thinking, though, that you might be able to apply that third tool, the shape recognition, to this. You might be able to say, I'm looking at it and it looks like a house with a slope roof this way or a slope roof that way, and I could learn that if it looks like this, I press this button. So for another experiment, we replicated this whole thing. We made one little change. Right over here, for these keys, we just changed the picture. So they look like this. And we said, think about it as having a house with a slope roof this way or a slope roof that way, and press the appropriate key. And the prediction is now you can use object recognition on the shape envelope across these two bars, and now you shouldn't have to move your eyes anymore, and the data should collapse into the middle, and that's exactly what happens where people are using this different tool, and it has a different signature in people's eye movements. So you have evidence for all three of these tools in the world's simplest data visualization. We're going to look at one example of how how this knowledge can explain slow processing versus fast processing in real data visualizations. Let's imagine that we have an intervention. We have we have person A or person B or group A or group B, and then we have them before or after some intervention. And you can look at these data, and I can ask you things like, on average, did this intervention work? Are people doing better before or after? And you can do that, but you might feel now that it takes a little bit of time to move your attention around to be able to figure that out. If you don't feel it there, maybe you feel it here. And if you don't feel it here, maybe you feel it here. So if I ask you, what's the mean effect of this intervention on average? How well does it work? Which participant had the biggest positive effect? Which participant had the biggest negative effect? What's the range of the effect sizes of this intervention? It's pretty tough to do because you have to use that slow comparison system to parse these data. So this is why you'd want to plot, if you care about the deltas, the relationships between these things, you want to depict the deltas directly. And now when you have so this one has dropped, so we're going to just code the drop. This one has increased, so we're going to code the increase. And now you can easily run statistics on these deltas. You can say that this is the min and this is the max, or that this is the range, or that this is the average in general. So that's why depicting these deltas is helpful, because it allows you to do these kinds of statistics on the deltas themselves instead of having to pull them out one by one. You might think you could do shape perception on this thing on the bottom. It's really hard in this case. You can only really do one shape at a time, and it's hard to average over shapes, so that mechanism doesn't work very well on the bottom. And this is all work from Christy Nothofer, who's a PhD student in the lab, to empirically show that this process on the top, using that system on the top, is going to make you orders of magnitude faster to pull out the information about the deltas. We were picking on shape perception a moment ago. Shape perception can be really helpful. It can confuse young students, but it can be really helpful for some people. Let's take an example of the connected scatter plot. So this is one of Amanda's visualizations from the New York Times. And we have on the upper left 2 time series line graphs. And so we have price of oil and oil consumption. And instead of showing those separately, we're going to get rid of time on both of them. So they're just 2 y-axes. And then we're going to connect those y-axes into a scatter plot like this, just to pair up the values. We've lost time. We're going to put time back by connecting those dots in temporal order with a line, so that you can still see the time component. Now that you understand what it is, here's the actual connected scatter plot. Maybe a little bit of xenographobia here, but I like these. And when you first look at this, so this is price of oil, this is world oil consumption, you can feel that slow comparison system that has to work. You have to go through and say, okay, price of oil is going up, but oil consumption's not changing, and then it's a slog to get through it. But after you've been staring at it for a little bit, shape perception starts to come online and give you a way to process this much more quickly. When I look at these now, I've stared at these long enough, whenever I see an L junction like that, I say, aha, the y-axis was changing, but the x was not, and now the x-axis is changing, but the y is not. And it's much quicker for me to get to that conclusion. I'm no longer unpacking that lower level of analysis. I'm just knee-jerking to the shape level and just using that as a direct connection to my expertise. How about a loop? What does a loop mean in a connected scatter plot? This one took me a while to wrap my head around. I actually had to tinker with these a little bit. But it's a time-delayed correlation. The y is changing, and then the x, and then it stops, but then the x changes in the same direction, and then the y goes down, and now the x changes in the same direction. These are actually used by economists to study economic cycles, or engineers to study pressure-volume relationships in engines. They're a great way of looking at time-delayed correlations, where if you imagine you had the correlation offset, where this one goes up and then this one goes, it can be a little hard to see with two line graphs at the same time. But now when I look at these, I know that there's a counterclockwise or a clockwise loop, and those mean different things. They indicate which axis was leading the time delay of the correlation. But I don't sit there and unpack the whole thing. If you're interested in these connected scatter plots, we did a whole paper exploring how well college students can understand and use them, along with Steve Harose and Robert Kosara. And if you go to Steve Harose's website, he has a fantastic JavaScript application where you can actually tinker with the points in one and watch how they move in the other. And that really helped me understand how these things work, to see the representations change at the same time. Finally, if you are using all of these tools flexibly, then once you've stared at the data for a long time and you get to be an expert in those particular data, you have a set of tools that you apply to a visualization, and when it comes time to explain those data to somebody else, they don't necessarily use the same tools. They don't necessarily see it like you do. And you get situations like this. Right, you've got a visualization, and this person knows exactly what she's doing. Nicole knows that when you're talking about this bullet up here, that bullet is supported by the ratio of this to this being bigger than the ratio of this to this. And she sees it differently from her audience, and that leads to communication failures because her audience doesn't see the same visualization. They see the duck while she's seeing the rabbit. This happens because your visual system, when you see different objects in the world, when you interpret patterns in different ways, it actually literally changes what you see. The picture in front of you is different. When you're looking at these berries, you can attend to just one berry at a time, or you can actually pay attention to all of the blue ones at once. So these distributions act not just as information providers, but you can also actually manipulate the world using them. So you can press one of these, and that causes all of the neurons that respond to blue things to have a higher activation level, which causes all the blue stuff to get sort of brighter and relatively inhibit everything else in the visual field. So you're actually changing what you see. If we were allowed to stick a little electrode in your primary visual cortex, like you can do with primates and other animals, you would see that the representation in your visual cortex for blue has increased and everything else has gone down. We're going to take away that activation, and now we're going to activate red instead, and the picture is going to change in your head so that you see the red but not the blue to a large degree. Same thing with visualizations. I could focus you on the bottom couple of lines, and as you're exploring these two lines, you're going to start turning switches in your head in order to have those lines pop out and everything else fade into the background to some degree. If you get interested in this line, you'll start to activate X junctions like this one and this one. You'll start to activate the darker color of those lines. You'll start to activate the particular orientations and the particular color of those lines, which causes those lines to pop out in your head and causes the other ones to fade out. You see this visualization differently. So knowledge and expertise literally can change what you see in one of these visualizations. It'll really make that duck or rabbit absolutely turn into a duck or a rabbit. We wanted to simulate this in lab because this is such a ubiquitous phenomenon in the world where an analyst or an expert gets too deep into the data and they go to explain it to other people, and other people have no idea what's happening, but the expert thinks that other people know what's happening. here's what we did. We took this visualization and we told a sort of juicy story. We said, well, there's 4 political parties, but only the top 3 get into the general election, so who cares about those top 2? The bottom 2 are struggling for that coveted 3rd spot. And what happened is the Green Party was leading the alliance over United, and then the alliance candidate accidentally insulted the spouse. We don't accidentally, I mean accidentally, right? Insulted the spouse of the United Party's candidate, and so their poll numbers came together. But then in a later debate, that other politician who was now almost about to take the lead didn't have a good answer to a question, so he tried to bring out the insult again, which made him look weak, and then they were separated again. So some juicy story like that. And then we say, forget about that story. We told you that. We have some cover story for why we told you that. We're testing out an experiment, something. We're going to grab that person from out there in the hallway that did not hear that story, and we're going to give them a clean copy of the visualization that looks like this. Can you please draw what they're going to find salient? Predict, if they were to draw on this graph, what would they say is the most salient, most interesting, most powerful part of this graph? And people can draw whatever they want, and they'll do something like this. And here is, now that's one participant's response. Here's everybody's. You can see there's a focus on the bottom here where these participants think that other people are going to see what they see on the visualization. Well, maybe that just is more salient, right? Maybe they're right, who knows? So that's just 1/3 of the subjects. So we took another 1/3 of the subjects, we told them the same story, but this time it was about the top 2 lines. We said the top 2 candidates were bickering, and then there was an insult, and then the other person didn't do well, etc. Told them the juicy story there, and in that case, here's what they predict about what other people are going to find most salient in the visualization. They think that other people are going to see what they see. We had another 1/3 of participants that focused on the green line here and the green line here. You can see they kind of come together and then they go apart again. Same thing, and you can see this is what they draw. And we said, remember, you know the story and they don't. Predict what someone else is going to see. The human mind cannot do that. You've got this particular representation of the visualization in your head. You cannot shut it off. There's this term called the curse of expertise or the curse of knowledge that's well known across the education world, where teachers have a hard time explaining things to other people because it's difficult to shut off your own knowledge and simulate the mind of a novice. It's the same thing with these visualizations. And this is all work from Cindy Xiong, a PhD student in the lab, and Lisanne van Wielden, who's a cognitive psychologist actually in the Netherlands who does data visualization consulting as well. And she noticed this problem in her own consulting practice where people would get deep into the data and then show things to clients that were not understood, but the consultant wouldn't realize that other people don't understand that. When you're showing data visualizations then, you can think of them as ambiguous figures. You can say, I need to disambiguate for my observer what they should see here. Whenever I teach data visualization to either undergrads or grads, we always tell them, think when you have a data visualization and it's time to communicate it quickly, what would Amanda do? Like Amanda Cox, what would she do? Amanda would show the carrot, right? She would disambiguate, and she would say, this is the way you should perceive these data. She would paint the way that these data should look to the observer. And that's exactly what outlets of the various data journalism outlets that are represented today are going to do when they've stared at these data for a long time, but they want the reader to be able to see what they see quickly. They're going to highlight the pattern, actually draw what they see to some degree, and then annotate it. And we saw a nice example of this, I think, yesterday from the Kevmanda collective, where we had nice annotation here, where there was a hard-to-understand visualization, and they know how to read it, but they had predicted that the reader might not, so they taught people how to read it with the highlighting annotation. This happens, this is one of the books that I teach with, where a lot of this book will show how to highlight particular trends and link them to particular points. And those of you that have seen Hans Rosling's presentation of data know that there's not a lot of highlighting and annotation on this display, but he knows that he's using 4-dimensional data that move in time, and that's a lot to take in, and he's extremely careful to use his language and enthusiastic gestures to keep you on task, to show you, and his main gesture is going to be, look at all these countries moving to the upper left. And he's really good at focusing you over time to let you see what he sees. So we've got this 2-bar graph. Again, that's our fruit fly. We're getting towards this level now, some of the new work in the lab. We're starting to look at shape perception in graphs. When you have something like this, how do you parse that in your head? How do you understand the shape of this stock graph? And if I took it away for a moment and I put it back, did anybody notice any changes in it? Right? So I made some subtle changes. I plotted the highs versus the lows, right? And I can make even more drastic changes in this, and you're not going to notice. The point is that you're not encoding this in your head like a picture. You're encoding it much more abstractly. And if we can define that space, create a model of what that looks like, then we could predict what you'll notice in a visualization and what you won't. And maybe there can be a computer-aided system that will help you notice, annotate what it knows you're not going to notice. Maybe you could set up a system where you could predict the level of detail that you should render a visualization. So don't keep querying that billion-row data farm database. Stop querying when you've created something that is beyond the limits of what the human visual system can parse in that particular visualization. So here's one way that it might look. We know that people parse shapes in the world by minima of curvature, right? That's how you cut this part into my arm, because there's the minima of curvature, and here's a minima of curvature. So maybe there's minima of curvature that serve as segmentation points for a shape. And we know that the human visual system is limited in how many pieces of an object it can parse at once. It's something like 3 or 4. So maybe you get something like that. And maybe your mental model of this thing at just a glance, if you just see it for a moment, is that it has a peak and it's a little bit curved like that, and it's skewed a little bit to the right. You can imagine the same thing here. Oh, there's some global texture that's laid out on top of this thing, but I changed the texture a moment ago. You didn't notice that it changed. I kept the texture's characteristics the same, but I changed the texture's positioning. You didn't notice, so you just know that there's a certain frequency on this thing, and then maybe the rest of the model looks like this. So this would be our goal, would be to come up with something where we could predict what you encode and what you don't. And then we hope to get there, but that's the 10-year goal. So to sum up, you've got many ways to see one visualization. There's a duck and a rabbit, and you've got 3 tools to parse the visualization, at least 3 tools to parse the visualization's data. You've got object recognition, which operates really quickly. And this can be a little bit dangerous for novices, but it's really helpful for expertise. It is the route to expertise, to learn how to see certain shapes in your data. You have feature distributions, where you can pick out these histograms, and you can do basic statistics on those distributions. And there's work to be done to decide where those statistics are veridical, like to the mathematical ones, or where they're biased and doing something a little bit different. And finally, there's this slow process of making comparisons over time, where you're comparing properties of individual objects. And this one takes on the order of seconds or even longer. There's a quote that I like from the graph comprehension literature from a researcher named Preeti Shah, where she says, understanding a visualization is not like just looking at a picture. It's like reading a paragraph. You're pulling off these sentences over time, and you can decide, expertise and instruction is going to teach you which sentences to pull off when, and which sentences answer the question that you're seeking to answer. But it takes time. It can take on the same amount of time as reading a paragraph. Make sure that, and be careful that you can see patterns in data that literally you'll see different things from other people, and the more you stare at it, the stronger that effect's going to get. You have that curse of expertise of being the analyst, and when you are worried about that and you need to communicate the patterns to others, you ask yourself, what would Amanda do? And you annotate and add that highlighting to sort of paint what you see in a visualization. I want to thank all the people that did all the work and all the people that paid for things. And I think I have a couple minutes left, so I will leave up this slide for questions, but otherwise, thanks.
Any questions?
Yeah.
Running up.
Hi, thanks for your talk. I'm from Gapminder, so it was great to see Hans Rosling's work there. You know us from animations as well, and I was wondering if you did any research on that, on perception of animations. You said a little bit like you can't compare it to pictures, and that's one thing we struggle with, but for example, changing position over time versus changing color or size over time of the bubbles, there's differences in how well people can see this, most likely. Is there any academic research on that?
This is like a planted question because we're starting a whole 4 or 5 year project on exactly this. Animations. So your visual system is really good at processing some types of motion. It's the kinds of motion that keep you from falling down, usually, right? So it's translation, looming and receding, right? Contracting and expanding, or rotational motion. You're really good at those. For other types of motion where objects move in arbitrary directions, it's a mess. Your visual system it does the same kind of statistical distribution analysis where you can say, well, the objects are moving dominantly up or dominantly to the right or mostly up and a little bit to the left, but who's moving where? You really can only process which object moved where for 1, maybe 2 objects. So animated visualizations all the way from education to journalism to any other kind of data display tend to use a lot of motion, but it's not clear how much the motion is adding to the information that you're getting into your head. It's definitely adding conceptual elements. You know that these objects that were here moved over here, that they're the same. You just know at a high level, but you could not tell me which is which. In the Rosling one, you know that the big blue one, you know that it was, I don't know, China, because it's big and blue, not because of the path that it traced. If we change the feature, you're gonna mistake it for another country. It was not the motion path that did that. The visual system is surprisingly bad at that. So we're going to explore the strengths and weaknesses of the visual system in moving displays and try to create guidelines for different kinds of motion. What speed can people handle? How many can people handle? What type of motion can people handle? To try to provide that as a model that people can use to stay within the constraints of the visual system. But otherwise, it's like the same limits as the comparison problem, where you just get one at a time.
Another question? She's on her way.
I've read quite a few studies on either networks or graphs and kind of doing eye tracking to see where things are. And I think there's a field in kind of advertising that does it. Have you done any research on, like, if you told someone a story and tried to train them how to read the visualization before they've actually seen it, if that helps at all or not?
So there's 2 relevant literatures here. I haven't done any of that research, but the 2 relevant literatures would, one, be the visual salience literature, where people have created predictive models based on natural scene statistics. Where are people going to move their eyes in a room like this? And those do pretty well. Those will explain 10, 20 something % of the variability in eye movements. But those don't do well in visualizations. So as soon as you get to a visualization, the scene statistics are completely different. It's mostly a white background. There's text that people attend to, which is high spatial frequency information that people in the natural world would never attend to. So there were a couple papers at IEEE Viz last year where people are exploring these salience models, and even a really cool tool that I know some researchers at MIT have come up with, where they train machine learning to understand that salience model, and you've got a real-time output of a heat map of where people will look on your graphic design or your data visualization. As you move things around, the heat map is changing. So there's some great potential applications for that. In terms of training people where their eye movements should go, that's done a bit for the graph comprehension literature in the education world. When you've got kids that are first understanding what a visualization is, and you want to train them to understand that there's an axis and that numbers are now bars, and it's the height of the bar but not the width that's important, and it's the top but not the bottom that's important, and training them to know just how to approach a visualization in the first place. There's some work with eye tracking there to diagnose whether kids are on the right track or not. But nothing with adults and the psychology side, to my knowledge.
Okay, one more, if we have one.
Hi, Steve. So you had the red, blue, red, blue, red, blue, blue, red, blue bar graph.
Yes, we do.
Does slow comparisons speed up if you know that you've got consistent red, blue, red, blue, red, blue, red, blue? So if you're not looking for that tricky pattern, if you've got the thing lined up, if you fix that, can you stop attending to the ordering?
There's dirty tricks. Yeah, if you know the structure of the data, there's all kinds of dirty tricks you can do. Absolutely. So if you know that all all the reds are lower than all the blues. Now you can just turn on the switch for the red to tune up the red. Just see that, get the mean of those. Same thing for the blue. Now you got the mean of the red, the mean of the blue, and you can subtract those, and you got the average mean delta. So there's ways that you can game this system, which are a scourge when we get to our experiments, and we have to show this kind of stuff because people always figure out ways around it. So exploring these tools requires that we figure out how people adapt some of these tools in ways that we wouldn't have expected.
Yeah, so please don't hide the book of dirty tricks, because
right.
we need to take advantage of it.
All right, dirty trick manual on the way. You got it.
All right, let's thank Steve.